Hello, welcome to NPTEL online certification course on Introduction to the Application of AI to Robotics. Today we are going to talk about nonlinear and time varying systems. You see, all manipulators, their basic equation is nonlinear in nature. Okay, we have already seen that when we were deriving the dynamic equation of the manipulator, and they are time varying as well. That is, many of the properties they vary with time. So, in today's lecture, we are going to see that what are the ways by which we can control such a manipulator. So, here I will introduce the topic to you, then we will see nonlinear and time varying approach, and the nonlinearity could be because of the spring, because of the friction, okay, and we will be seeing an example of inverted pendulum, which is a single degree of freedom manipulator, and then we will be seeing the control of inverted pendulum, say using Python, and then we will try to understand the multi-input, multi-output control system, because you know a robot is consisting of multiple number of joints. Okay, so how can we treat that multi-input, multi-output control system? Okay, so you see, in earlier robot control model which we have seen, each joint was often considered as an independent linear constant coefficient second order differential equation. This is how we have seen, and because of that only we have seen the whole treatment of the second order differential equation, okay, and the three cases, that is the over damped, critical damped as well as the under damped cases we have seen. Okay, so this concept was useful for the linear analysis, okay, and which relies on the assumption that inertia seen by each joint actuator was constant. But you see, in case of a real manipulator, this is not true. Okay, the inertia changes with configuration, coupling between joint varies with motion, and the damping and dynamic effects are not uniform across the workspace. Okay, so these are the some of the factors which are real challenging in nature. So, this is the nonlinear dynamic equation of the manipulator we have seen. Okay. So, if we look at say the inertia matrix here, okay, you see it is symmetric, positive definite, position dependent, okay, because it is function of theta, and the robot's mass changes with configuration. This is what I said in the previous slide. Okay. Then we have Coriolis and centripetal part of it. Okay, you see there are velocity dependent coupling forces between joint, alright, and it vanishes when your manipulator is at rest. Then we have the gravity vector, okay, that is the torque needed to hold the arm against gravity, and it is very highly position dependent. And coming to the external torque, it is a contact forces basically. As payload changes, disturbances are there, they are unknown and time varying. Okay, so all these factors contribute to the non-linearity in the manipulator dynamics. Then we have the time varying nature of this manipulator system. For example, the payload changes. When a robot end effector picks an object, okay, its inertia is different, and when that object is dropped, the inertia is different. Alright. So, a fixed controller design for empty hand will fail if we are using it for the payload. Then we have wear and friction. Joint frictions are there, you may have backlashes in the gearboxes which are used with the motors. Okay. Stiffness changes over time with mechanical wear, and calibration becomes outdated many times. So, these are the factors which are time varying. Alright, you may have thermal effects, okay, that is motor heating changes winding resistance affecting the torque output. Then we may have external interactions. Suppose a robot is being used with the co-workers, okay, and we have the human robot interaction, okay. So, your interaction forces may be unknown, alright, time varying contact forces not captured the design time. So, all these possibilities are there. Alright, and that is how the time varying nature of the manipulator comes into the picture. Okay, here is the example of a KUKA robot. Here you see the different configuration here where this arm is horizontal and here it is in this position and here you have some end effector load. Okay, so you see here inertia changes with varying configuration. Okay. So, all these things motivate us to study the nonlinear and time varying control methods for a manipulator. Okay. So, in this lecture we will base out our controller design directly on say n cross 1 nonlinear vector differential equation of motion. Okay. Now, before we proceed further, let us look at what are the ways by which we can approach a nonlinear problem. Okay. What are the common linearization approaches which we can apply? Alright. So, there are two approaches basically. The one is that one where we can do the local linearization and we could also have the moving linearization. Alright. In case of a local linearization, linearization is done around an operating point as all of we know. Okay. And in case of the moving one, we have the operating point changes as the name indicate basically. Okay. So, it changes continuously as the system moves. Okay. And this approximation is true basically near that operating point. Okay. And here the system is continuously relinearized around the point. Okay, because it is moving. Alright, and here the robot manipulator moves through a wide workspace, okay, and this one maintains better approximation during motion. Okay. So, here in case of local linearization problem is that you see when the robot moves, okay, its dynamic changes with the configuration. So, approximation that you have a single operating point, that is not very correct. Okay. So, because of that we have issues, we have errors in our model. This one, that is the moving linearization, its result in linear but time varying systems. Okay. It is useful in analysis, still it approximates the nonlinear system. Okay. So, what could be the nonlinear time varying approach? You see for nonlinear control, one of the important idea here which we are going to see is that can we have a control law such that nonlinearity in the model can be cancelled by that control law. Okay. So, that the closed loop system becomes a simpler one. Okay. And that is why we call this approach as the linearizing control law. Alright. And you see the fixed gain cannot keep the system at one desired pole location such as critical damping, that is of course all of us know that. Okay. So, a better approach is to use the time varying gains, okay, that changes with the system state, and this keeps the overall stiffness or response behavior approximately constant. So, the approach of the partition control law which we used earlier in the linear control as well, okay, we can use the same partition control law approach here, and here you see the servo part will remain unchanged what we have seen earlier, while the model based part will be able to handle the nonlinear dynamics. Okay. So, this is how we are going to tackle the nonlinearity in the robot model. Okay. So, first of all let us see the nonlinearity could be because of spring, right. So, the model which we have seen earlier, okay, to study the behavior, we have seen the say simple spring mass damper system, right. So, in that one if your spring is nonlinear, right, you see for a linear spring, okay, the force increases, okay, proportionally with the displacement and your stiffness remains constant. But if you have a nonlinear spring, your force and displacement relationship is no longer a straight line. Okay. So, here this curve represents force as equal to q into displacement to the power 3. Okay. So, the nonlinearity in the system is introduced by spring. Okay. So, here in this case what will happen? The force will increase nonlinearly, okay, and effective stiffness change with displacement is going to be there, and this type of behavior, okay, is common in case of flexible joints or your compliant mechanisms and the robotic manipulators. Okay, so this is what I was talking about. Okay, so we have a spring mass and the friction here which behaves as a damper. So this is the reference direction x1. Now suppose if I want to control the position of this mass, say I apply a force F on this system, right. So to analyze, I can draw a free body diagram here. So in this free body diagram for a displacement x, this is the spring force, right, which will be opposite to the direction of displacement. This is the force of friction being modeled as a viscous friction over here, again opposite to the direction of displacement, and this is the direction in which we want to apply a force in order to control the motion of this mass. Alright. So if I write the expression for the unbalanced forces in this direction, right. So it will be this one minus q x cube minus b x dot, right, and say what, plus f, and these are responsible for your acceleration. Okay, f I could include here. Okay, so this will be your mx double dot. So this basically gives me what, mx double dot plus bx dot plus qx cube is equal to f, this equation. Okay, so we need to construct a control law now here, this f, alright, to keep the system critically damped with a stiffness, say some KCl critical, right. So to do that, this is my equation of motion for the system. Okay. So here the partition based control law, we can propose a model based portion f as alpha f dash plus beta, same as what we have seen earlier. Here alpha is your m and this beta is whatever is over here. Okay. So this is bx dot plus qx cube, and we will see that by assuming beta as this one, we will be able to cancel out this qx cube, that is the non-linear part, okay, because the same is there in the equation and the same I am considering over here in the model based portion. Okay. So what my f becomes, this one, that is my m f dash plus b x dot plus q x cube, alright. And I can assume this f dash, that is my servo portion, as xd double dot plus kve dot plus kpe. Here your kp is proportional gain, kv is derivative gain, e is the error, e dot is the derivative of the error, and error is defined as basically the desired minus the current one, actual one, alright. And so, and this is your desired double derivative. So now what we can do here is that, so this is my expression, that is the dynamic equation for this system, and here I am substituting for this f as this one, right, and this is same as which I derived over here. Okay. So I have done, and now if I substitute it here, you will see that this portion will get cancelled here, this one will get cancelled this way. Okay. So this is the what you are left with, and so m1 get cancelled. So you have x double dot as f dash, and now I can substitute for this servo law. Okay, that is f dash is this one, and when I substitute this, I can take this x double dot towards the right hand side, and what I will be getting basically the error double derivative, right. So this is what I get. Okay. So here you see what has happened, system now behaves like a linearized second order system, and by choosing the appropriate value of Kp and Kv, okay, I can get the desired damping, and then I can get the critical damping is possible, and in this way my closed loop poles remain fixed. This figure basically shows the implementation of this one. Okay. So this is your system basically. Okay. So I take x dot and x here through sensor, I take these values out, and then through x dot I evaluate bx dot, and through x I evaluate qx cube. I sum them up, send them here, and x dot is here, so I send xd derivative. This I get from my trajectory generator, okay, which generates position, velocity and acceleration, that is the desired one. So, I get the error here, multiply it with the kV, that is the gain, add up here. Similarly, I get xd here, x here, subtract it, get the error, multiply with gain kp and sum them here with xd double dot. So, this is what I get as f dash. Okay. So, it is this f dash which I get over here. So, xd double dot plus kve dot plus kpe, and now I multiply this f dash with m and then I add up with this portion. Okay. So, essentially this is my your servo part and this one is my your model based part, okay, and this way I try to control my system. Okay. Next, let us see the non-linearity because of the friction. Okay. So, we can take the case of Coulomb friction. So, in manipulator the friction of the joint in its bearing, okay, whether it is a rotational or linear joint, okay, is modeled more accurately by the following non-linear characteristic, okay, than by simple linear model. Okay. So, the linear friction is this one, basically friction coefficient into the velocity, and we can have the Coulomb friction as well. So, Coulomb friction coefficient into sine of x dot, okay, where at when x dot is 0 this value is 0, x dot greater than 0 this is plus 1 and x dot less than 0 it is minus 1. So, this is what it has been shown over here. Okay. So, this is for x dot greater than 0 you have this value, okay, and x dot less than 0 you have this value minus Bc. Okay. So, here we can carry out the similar analysis which we have done for the case of the non-linear spring, okay, and yeah. So, this is my system, I draw a free body diagram, and so spring here I am assuming to be the linear one, okay, but the damping I am assuming that is to be the non-linear one, okay. So, I can write the open loop equation, alright. So, assuming the Coulomb friction, okay, and here we will try to cancel the non-linear friction using the model based control. So, again we propose the same control law, the model based control, where alpha is m and beta is this one basically, right. So, my f becomes this one and this is the servo part same as that one, alright. And to put it together, this is my equation of motion, right. This is my model based control basically. So, here you see that in this control law I have taken care of these two part of the model, okay, and this is my alpha basically into f dash, where my f dash is what my that is the servo part, okay. So, if I substitute this f over here, okay, so you can see that this gets cancelled. Okay, so this non-linearity basically getting cancelled, this is non-linearity in the model, this is getting cancelled by the non-linearity in the control law, okay. This kx gets cancelled similarly. So, what I have is this one, and so again I get the same expression, okay. And now I can substitute my servo portion over here, okay. So, I get this the final closed loop equation as this one. Okay, it is the same equation which we have seen previously, okay. So, it is a standard second order system, linear second order system, and gains Kp and Kv determine the damping behavior, okay. So, as we have seen that our aim is always to have a critical damping, so that we get the fastest response, okay. So, we can get that critical damping behavior by choosing the appropriate value of Kp and Kv over here, okay. Next, let us look at an inverted pendulum, okay. So, in this case basically what we are trying to look at the non-linear nature because of the inertia, okay. So here this is my say single degree of freedom manipulator, okay, which is basically an inverted pendulum over here. So say this is the length of that, you have a mass m at the tip, and this is the coordinate theta, and this is the direction of g. Okay. So this motion is not simple because inertia depends on the link geometry, as I said. Okay, and say we could also assume that the friction is non-linear. Okay, so this system is not a linear second order system. Okay, so to generalize this, I can assume that the joint has viscous friction as well as the Coulomb friction, and that is the way to make your friction modeling more generalized and more realistic. So in this case, what is going to be this torque basically? Okay, so you see this is going to be here the weight of this one because of the mass at the tip, and you see this angle is theta, so this angle is going to be, I can draw it like this, this is 90, so this is 90 minus theta, so this angle is going to be your theta, right. So this you are going to have a component here which is mg cos theta, okay, and this mg cos theta into L is going to give you the torque here. Okay, so this mg L cos theta, this is the torque over here. Okay, so because of this weight, and then what else is there in this system? You have the friction modeling, the Coulomb friction and the viscous friction model. Okay, and you have this one, that is the inertia because of this one mass. Okay, so its rotary inertia will be actually ml square about this point. Okay, and this theta double dot, and this all is going to be equal to tau, that is the torque which we are applying. Alright, so this is the nonlinear equation of this single degree of freedom manipulator, right. So here to control this one, again we can have the partition control law here, alpha f dash plus beta. Now here alpha is basically here is going to be equal to the coefficient of theta double dot. Okay, so I can take alpha as ml square, and rest of the portion here will be forming my beta. Okay, so this is my beta. Okay, now so if I write the model based law, so it will be basically tau as ml square f dash plus this one, and when I substitute this one over here in this equation, alright, so this is what happens. Okay, so this is what I will be getting over here, and we have theta double dot as f dash, and f dash I can substitute as this one, same the servo law. Alright, and so with that we will be getting this equation basically. Alright. So if I want to explain it through the block diagram, you see this is my system basically, a single degree of freedom manipulator with the mass at the tip or weight at the tip. Okay, so I get the theta and theta dot values from here, alright, and I try to evaluate beta using this theta and theta dot. Okay, and this theta dot and theta d desired, I am subtracting them in order to get the error derivative here. Okay, and multiply it with gain kV, send it over here. Similarly, I get theta from here, theta d from here, I find out the error, multiply with the gain, and then I send it over here, and this is theta d double dot I am getting from my trajectory generator. So this value and this value I am getting from my trajectory generator. Okay, so I add them up, so this actually constitute the tau dash, I multiply with ml square and then I add with the beta, so I get basically my tau in this case. Okay, and so this is how the system is. Okay, now let us try to have a feel of this control problem. Okay, so I am presenting here a small Python simulation. Okay, so we have desired angle, what angle we want, desired angular velocity, desired acceleration. Suppose desired angle we want 90 degree, okay, and desired velocity and acceleration we want 0, 0. Okay. So here we specify link parameters, say mass 1 kg, link length 1 meter, I can evaluate the value of I. Now here I am specifying these values, okay, C, V and G which are there in my model, and say I am taking these control gains. Okay. So, basically, so here I define these as say x, and here I am defining these desired values. I am tracking error, okay, error derivative here, alright, and so this is my f prime basically, and this is my expression for the tau. So, this expression is basically same as this one which we have seen. Okay. So, here the function called upon the control torque function to calculate theta double dot. So, basically from here we try to find out the theta double dot. So, this is basically tau minus this one minus this one minus this one. So, basically this is the theta double dot which I am trying to evaluate over here. Okay. And so, this all divided by I, and then we can solve this plant dynamics. Okay. So, here is the, you see the angle, okay, basically we are trying to take it to the 90-degree, and you see that this is the plot versus time. Okay. So, theta d is this one. So, this is my desired one, okay, and this is my the actual one, actually this is theta t. So, it starts from 0 and then it goes to 90-degree, and here are the errors basically. So, you see that error initially you have a large amount of error because your actual manipulator is at 0-degree and you want 90-degree, okay, and this is the derivative of the error, and this is how the torque is needed. Okay. So, this is the animation which you can see here. So, this went from 0-degree till 90-degree. Okay. So, you have the desired, this is the desired one and this is the actual one, and this is the face portrait for that. Okay. Next, let us see, as you know, a manipulator has got number of joints, right. So, it is a multi-input, multi-output control system. Okay. So, till now we have been considering a single joint, and in fact, I have shown you the single degree of freedom manipulator, okay, which is the inverted pendulum. Alright, but the actual manipulator arm are going to have the number of degrees of freedom. Okay. So, the system is not one equation in that case, but you may be having many coupled equation, and input and outputs are both vectors there. Okay. So, earlier we were having single input single output system, but now we are going to have the multi input multi output system. Okay. So, what we need to control? We need to control again the joint position, joint velocity and the joint acceleration. Okay. And what we should get? We should get the vector of actuator torque or forces. Alright. So, here again we can have the same control law which we have seen earlier, the model based portion. Now, here the difference is that here this f dash is going to be n cross 1 vector of servo, beta is again n cross 1 vector, and your f is n cross 1 vector, and your alpha is going to be a n cross n matrix. Okay. Alpha need not be diagonal. Okay. And it is chosen to decouple the couple equation of motion, and if alpha and beta are chosen correctly, each joint behaves like an independent unit of mass. Okay. And the nonlinear system becomes easy to control. Okay. And so, hence it is what we have been discussing earlier, linearizing and decoupling control law. Okay. So, this is our servo portion, right, the same one which we have seen. Again, the thing is that here, okay, it is a multi-dimension basically. Okay. And in this one, these are the gain matrices, okay, velocity error vector, position error vector and desired joint position vector, and your gains are basically in the form of a matrix like this. Okay. So, to summarize here, what all we have seen? We have studied the limitation of the linear constant coefficient manipulator model. I introduced the nonlinear and time varying control approaches for the manipulator. Okay. We have learned the concept of linearizing control law and the partition control law. We have seen the case of nonlinear spring, nonlinear damping, okay, as well as that single degree of freedom manipulator case we have seen. Okay. And yeah, we have seen the implementation for the inverted pendulum using Python, and then we extended this concept to multi input multi output system. Okay. So, with this I would like to conclude. These are the references which you can see, and thank you.